Hello, welcome back. We're in the second video for Chapter 4, and we left off, we have a new topic. We're talking about concentration. So what is concentration? Concentration means amount per volume. So perhaps you go in the grocery store and you've bought that tube of orange juice in the freezer section. And what does it say? It says orange juice concentrate. You take that, you throw it into a pitcher, dilute it with water. So what is that? That little tiny tube of orange juice has all the orange juice goodness of an entire pitcher of orange juice. So concentrated, it's concentrated. It means there's more amount per volume. And there are some other concentrations like the proof for alcoholic beverages. So if something is 80 proof, for instance, that means it is 40% alcohol by volume. So we don't use that one's used in the liquor realm. We use a different type of unit in chemistry. We use the term molarity. And molarity means moles per liter. So for instance, 36.45 grams of hydrochloric acid, that's 1 mole of hydrochloric acid. You dissolve that into a final volume of 1 liter of water. That means it's a 1 mole per liter hydrochloric acid in water. So let's look at this. Here's an example. Suppose you dissolve 25.5 grams of potassium bromide to make 1.7 liters of water. What is the molarity of the solution? So let's look at this. 25.5 grams potassium bromide. So potassium is 39.1. Bromine is 79.9, I think. I should look at this. Okay, bromine 79.9, potassium 39.1. Okay, I am correct. So add the 1, so that's 80 plus 39. That is 119 grams per mole. So, sorry for the aside there. Mole KBR, 119 grams KBR, and then 1.75 liters. Now, if you look at these units cancel, and you're left with mole KBR per liter, and then just dividing that through 25.5 divided by 119, you get 0.214 molar KBR. KBR, potassium bromide. So that's how you do a problem like that. And let's look at this problem. So 50 milliliters of half molar will make what concentration at 200 milliliters? Now there's a trick here. Molar 1, volume 1 equals molar 2, volume 2. You might also see it C1V1 equals C2V2. That's another way you can do that. The way you do this, so it's 50 milliliters. It can be any, so 50, actually I should do concentration first. So 0.5 molar 50 milliliters equals our unknown concentration times 200, and then you can just 200 there, get rid of that, and then you solve for, so now you do the calculation there, and that's just this is going to be 0.125 because you've diluted it 4 times. So for me, I look at 50 milliliters, 200 milliliters. It means it's diluted 4 times. That means you divide it by 4. So 0.5 divided by 4. Well, it's half of a quarter, which is an eighth. So that's just how I see math. You can put in your calculator, get the right answer. You'll get the same answer. But you know, if you see the math tricks, use them. Okay. So next thing we're talking about is solvent and solute, and I am using alcohol because it's a legal substance. So I've seen this in my teaching evaluations before. I'm not advocating drinking, I'm advocating chemistry. And I'm using alcoholic beverages because they are real-world examples that are legal. Okay, so the solvent is what is the most of. It's what does the dissolving. The solute is the least of something, is what's being dissolved. So I have a list of alcoholic beverages here with approximate concentrations. I know there's other stuff and things, but let's just assume beer is just alcohol and water. Beer it can range in concentration, but we'll say 6%. 6% alcohol. That means that the rest water, 94% water. What is the solvent? The solvent is water. Beer is a little bit of alcohol and a bunch of water. Wine, 13%. You look at that. What's the most? Water. Wine is mostly water with a little bit of alcohol dissolved. Now look at vodka. Vodka is typically 80 proof, which is 40% alcohol. But, lo and behold, water is, in fact, the solvent still. So I've heard people going out and they say, this bartender is cool, he gave me a drink, it's just like straight alcohol. Like, if it's vodka, nope. Your vodka cranberry is still mostly water. Doesn't really hydrate you, but it's still water. Mostly. Solvent, at least. Then you can have absinthe. Absinthe depends on the type. You can get as high as 70%. Now 70% here. Now alcohol is the solvent and water is the solute. And 151 proof, you get on to grain alcohol, which is 95% alcohol and 5% water. Now, grain alcohol is another concentration, a special case called an azeotrope, where the vapor concentration is the same thing as the liquid concentration. So for alcohol and water solutions, you cannot purify it past 95% alcohol percentage. There's ways you can do it. You can push that through a molecular sieve, and it'll push all the water out. You can put something in, it'll absorb water. People tend not to do that, though. It's kind of expensive. The materials are kind of expensive. You could add something else, and then separate the mixture and get that, and get the water out of that, and then separate it again to get the other stuff out. That's how they used to do it, but typically they use something like methanol or benzene, which is pretty toxic. So molecular sieve is the way to go, at least if you want to drink it. That's typically what they do for gasoline alcohol anyways. So hopefully you understand now the solvent and the solute. The most is the solvent, and what is being dissolved, the least amount is the solute. And we're going to talk more about aqueous solutions in 162. But let's talk about aqueous solutions. So what is a solution is the first thing I should start. A solution is a homogeneous mixture. And we have, and these are all water, liquid solutions, specifically water solutions. Electrolytes. It's not just what plants crave. Electrolytes mean it conducts electricity. So water, pure water, is considered a non-electrolyte. It's a it can a little bit, it's a very weak electrolyte. But there are strong electrolytes, so strong acids and strong bases, those are strong electrolytes. They break apart, they conduct electricity really well. Salt and other salts, these soluble salts, are strong electrolytes. Weak electrolytes are things like weak acids and weak bases, like vinegar. Vinegar is a weak acid. So this picture here, you have a battery and you have a light bulb. That's a strong electrolyte that conducts electricity. So sugar there, it's a non-electrolyte, does not conduct electricity. You put vinegar in there, the light would turn on ever so slightly. So that's a weak electrolyte. Has to do with conduction of electricity. Okay, so let's go and talk about solubility of salts. So there's two words for salts, or definitions. There's two definitions for salts. One is a metal and a non-metal that's not an oxide or hydroxide. So that's one definition. The other definition is the result of a acid-base neutralization reaction. So acids taste sour, bases taste bitter. What does salt taste like? Well, sodium chloride salt tastes salty. Doesn't taste sour, doesn't taste bitter. So what is sour? So sour is like lemon. That's a sour flavor. That's citric acid. What's bitter? Base, cold and calcium, strontium, and barium, the resulting compound is slightly soluble. Not very much, though. It's really not that soluble. And then carbonate and phosphate, these tend to be insoluble. And the exception are alkalis and ammonium. So you're like, why are some soluble and why some are not? This has to do, so when you put a solid salt in water, the water rips it apart. Later on you learn water has positive and negative ends. And the idea is the reason why in general it does this is because there's more of an attraction between the water, the charges in the water and the charges in the salt. So lithium, sodium, potassium, they're all big ions and they're all +1 charged. So if you have a higher charge and you have a more tightly bound polyatomic ion, it's not going to be ripped apart by water. That's the so what in this. But the point of this is to teach you logic. So let's see here. Let's determine whether or not this is soluble. So if you look at the first one, lead chloride. So you look here, chloride's here. Chloride tends to be soluble, with the exception of lead. Oh, because of that, it's insoluble. I'm putting down arrow, meaning it forms a precipitate. Oh, is this soluble or insoluble? Okay, it's insoluble. I'll put a solid. It's insoluble. Copper chloride. So the copper for chlorides tend to be soluble. Silver, mercury, lead. Copper is not one of the exceptions. Actually, I'm going to call this insoluble. We'll call that insoluble. We'll call this soluble. Okay, calcium nitrate is the next one. All nitrates are soluble. So right here, this one, all nitrates are soluble. So this means soluble. Barium sulfate. Sulfates tend to be soluble, but barium is exception. So this one is insoluble. And I drank that, as a matter of fact, when I got a CT scan once. So tastes terrible. Kind of chalky. Okay, next one, precipitation reactions. So you mix two liquids together and this stuff falls out of solution. So that is a precipitation reaction. And it is a chemical reaction because you had two things that could dissolve in water and you've created a new thing that did not dissolve in water. And I haven't talked too much about the periodic table, but with the periodic table, this first row here, these elements, they're also known as the alkalis. Alkali means basic, like the opposite of acidic. These are known as the alkaline earths. So they're basic metals. You throw them in water, it forms an alkaline solution, a basic solution, and they're called earths because when you mix chemicals with them, they tend to form precipitate. You have water. This is the old earth, wind, fire, water kind of thing. You have water and you pour them together and you get dirt, you get earth, you get a precipitate. So they're alkaline earths because they have more precipitates than the alkali metals. Okay, but let's write a reaction for precipitate reactions and predict them. Now I'm just using this as an example. I'm not trying to promote heteronormality, but it's easy to explain it. So it's kind of like with potassium carbonate, it's like you have a couple and you have unlike charges, and then it mixes with nickel chloride to form another couple of sorts. So it's like a partner exchange reaction. And so you have to look and think, okay, is one of these two insoluble? So for the first one, let's say you have potassium is then going to mix with chlorine. And all potassium salts are soluble, so that's not going to result in a reaction. Then nickel is going to react with carbonate. And if you look at the rules for carbonate tends to be insoluble. So carbonates tend to be insoluble, and nickel is not an exception. Therefore, this one will form nickel plus 2 carbonate. So, by equation precipitation, okay, so it's nickel carbonate and then plus 2 potassium chloride. So, that's this is aqueous. Let me write this bigger for you. K2CO3 plus Ni, I should do the aqueous. Aqueous plus nickel Cl2 aqueous yields nickel carbonate solid plus KCl aqueous. And if you balance this, so 2 potassiums on the left, 2 potassiums on the right, 1 carbon on the left, 1 carbon on the right. I know I'm just using the ion. That's no shortcut. I'm not using carbon and oxygen. You can use the groupings if you want as well, unless they break apart. Then nickel, 1 nickel left, 1 nickel right, 2 chlorines left, 2 chlorines right. So, balanced. Okay, next one, sodium nitrite. Nitrate, excuse me. Sodium nitrate and lithium sulfate. Well, if you remember the rules, all alkalis are soluble, so this is going to be no reaction. This is going to do absolutely nothing, no chemical reaction. Okay, so let's look at the sample. Copper chloride and lead nitrate is what's made. So right here, this one here, you have two negative ions. That's not going to mix. That one's wrong. So if you look at this, you're either going to make copper nitrate or you're going to make lead chloride. And all nitrates are soluble, and chloride's going to be soluble, but lead plus 2 is one of the exceptions. So you make the lead plus 2 chloride. And we are done with this video. So I will see you for the third one.